Bismillahirrahmanirrahim, students. I am your course instructor Muhammad Kashif, and the course name is Design and Analysis of Algorithm. In today's lecture, we are going to start another topic, that is graph. And before I start my lecture, I want to give you a quick overview that we've covered in previous lecture. In previous lecture, we have written the algorithm related to the heap, and we build an algorithm for max heap, and we have write a piece of code for delete function and to build a heap. And in previous lectures, you have seen that, or you have observed that our problem is going to traverse in log of n time complexity, and you know that when our problems are going to traverse in log of n time complexity, that solutions considered as a good solution. So we have seen so many problems related to the trees, and our problems are simulated in the form of tree. So a graph is another advanced form of uh, uh, problem where we can represent our situation into form of tree. So in real life, you have observed so many situations, you have observed so many places where graph actually exist. So when we talk about the route planning, when we move on roads, when we use a Google map, or when we find a shortest path, this graph theory actually exists there. That means our problem is going to convert into the form of graphs. So because in graph we have different nodes, we have edges. So because we start from a point and we need to reach out on a certain place, or on a position where there exists an edge. So graph is very important when we implement problems that recursively, or you can say divided into multiple sections or in a multiple nodes. So in today's lecture, what will you learn? You will learn what is a graph, and we will cover types of graphs and applications of graph. So first of all, we need to know what is graph. As you can see, we have multiple nodes, we have different nodes in a graph, let's say A, B, C, D, E, F, or G. You can consider this graph, these nodes as multiple points, multiple locations, or sources or destinations. That means we have multiple nodes, and these nodes are connected with the solid lines. These lines are called basically edges, and each you can see each node is connected with another node, except a few of them. Indirectly we can access multiple nodes via different nodes, but this is a graph, this is type of graph, and we will see what type of graph is this. But for now, you just need to understand what is the definition of graph. So graph means we have edges, we have vertices, and we have edges. So vertices means the nodes, and edges means the solid lines that are connected between two nodes. So both are belongs to the edges, where u and v belongs to vertices. So this actually mathematical notation that represents the relationship between edges and nodes. So u and v both variables, or you can say the parameters, are belong to the edge, because if there doesn't exist an edge, two nodes cannot be connected with each other. And when two nodes are connected, we can say we make a graph. That is a graph when two nodes are connected. And without an edge, nodes cannot be connected with each other. So that's why this is the main definition of graph, where edges and vertices are belongs to the edges. So how do graph differ? What are graph characteristics we might care about? So first of all, in our real life, as I told you, that in our real life, graph exists everywhere. While we are making electronic circuits, while we are making embedded programming, like we are planning to find the shortest path in air flights, or you can say in railway tracks. You can see this example in your when you are traveling from one place to another place. You find the shortest path, you find the shortest route where you want to move, so that you can save money, you can save your time. So this is the main ultimate objective, to find the shortest path. Why graph theory help you to find the minimum cost, minimum time to solve your problem? Because we this is a graph theory that we can implement, that we can use to design computer systems, we can use for computer applications. Because we have in current paradigm, we have an objective to reduce the cost, we need to reduce the time complexity of our algorithms. And we will see in later lectures that in graph theory, what type of algorithms we can use to you know reduce the cost, and how we can solve our complex systems by using graph theory. So different type of, if we talk about the types of graph, we have undirected graph, we have directed graphs. So in this particular slide, you can see we have undirected graph. Edges do not have any direction. As you can see, if A is connected with B, A is connected with D, there doesn't exist any direction. There they do not have any direction in between, because we if we want to move from A to B, we can move. If we want to move from A to E, then definitely there must be a mediator in between A and E, that is D. But the main part is there is no direction available in this graph, and that graph is called undirected graph, right? Because in most of the situation, we have directions, but in certain in some problems, we do not need to use direction. So we have directed graphs. But in this particular slide, we have directed graph, in which you can see the arrow signs are available. We have direction from B to A. That point, it points actually because we are moving from B to A. And if we want to move from B to D, there is a direction, and there is a cyclic path available on a A. If you can see, it's basically a loop. When we want to reach on a particular location again and again. And obviously, you can see in your real life, if we want to move, we want to visit a place again and again, that means that node or that location is visited in a loop, right? So this is a directed graph, and you can see on each node there is an edge, and edge has a direction, edge pointing out the direction from the source node and to the destination node, whether we are moving from D to E, or E to F, E to G, and D to C. Each node has a communication via directed nodes. Another type of graph is basically weighted graph. And in this particular problem, or on a slide, you can see each node is connected with edge, but edges has weight, right? Why we are putting the weight over here? because we relate this topic to our daily life problems, in which we want to move from one location to another location, where we use calculations, where we analyze ourselves whether we are using a shortest path or not, whether we are saving the money or not. That means if I am moving from A to B, then definitely I will calculate the cost of that particular path, whether it could be a money, it could be a time. But there is a parameter that can be used to evaluate, that can be used to judge the cost between two connecting points. So that's why we are using weight over here, and this is called a weighted graph, in which edges have some weights, and weight represents the cost between two communicating nodes, and it gives you an idea which node has a shortest path, or which node has a longer path. Then weighted and directed graph. If we have weights on edges, then definitely we can have direction on each node. That means if we bound a user, if we bound the object to move from a location, and we have to assign a proper destination, then he or she has to follow that direction. And direction actually bound you, or this is a constraint in your applications, that allow you to move from, or to drag from one screen to another screen. And you can use, or you can see in multiple web applications, or mobile applications, in which you can observe this particular application of graph, where you restrict or you bound to proceed a process, or you use the guidelines or policies. And if you do not follow the rules and guidelines, you are not allowed to enter in the application. For example, you cannot log into the system without registration. You cannot enter to the system without providing your username or password. That means there are directions that you have to follow while you are dealing with software applications. So and if we are relating graph theory with our software applications, that means we have directions, we have policies, we have guidelines to implement or to use software applications. Next, terminology. A path is basically a list of vertices that exist on an edge. For example, there is a path. If we talk about, if we want to reach from A to G, then there are multiple vertices that are related or linked in this path. So path is basically just simple a terminology that represents the number of vertices that include in a particular path. That means we use multiple paths, and in multiple paths we have multiple edges. As you can see, if I want to move from A to B, D, E, and F, that means this is particular path in which A, B, D, E, F are the edges or the nodes that include in this particular path. Then if I want to move from D to C, and in this particular path I only have two nodes, and that are C and D, and these are basically belongs to E, because in our early slides we have seen and we studied that all the vertices and edges belong to the edge, because if edge do not exist, then path cannot be exist. Then a path has a list of vertices, and where there exist an edges belongs to edges. A simple path contains no repeated vertices. Often this is is referred to as a simple path. implied. That means there is no repetition. As you can see, we do not have any cyclic path. We do not have any loop on any particular node. So this is a simple path. But what is cycle? Cycle means an action or a process that can be done repeatedly, a subset of edges that form a path such that the first node and end with the same node. There should be a path, and that path would be a cyclic path. So this is a cycle. That means if we start from one position and end with that same position, that means there exists a cyclic path. As you can see over here, if we connect A, B, and D, there is a cycle. There is, a path where if we start from A, then we can end it with A. And if we start with B, we can end with B. And if we start with D, we can again come back to the D. So there exists a cycle. But this cyclic path, this type of path does not exist on any other node, as you can see, right? Because on any other nodes, we cannot see any cyclic path over here. So it's not a cycle. If we just talk about A or B, this is not a cycle, right? But when we include D, then we can say this is a cycle. So this is an example where we cannot consider these two nodes. uh, these two nodes doesn't have any cycle, right? And if we see on this slide, if we can see, there is a cycle, and again it's a directed path, directed plus cyclic path. Because if all right, a subset of edges that form a path such that the first and last node are the same. But we can see if we start with from B, and we can go to the A, and from B we can go to the D, and from D we can go to the A, but we cannot come back to the point B. That means there does not exist a path, not a cycle, right? So it's not a cycle, but it's a directed graph. But directions are in a way that do not allow us to move in the form of cycle, right? So now you can see this is a cycle, and it's a directed graph where if we start from A, we can move from A to B, and we can go to D via B, and obviously we can move from D to A, and again we start from A, we again can come back on A. So there is a directed graph, and it's a cyclic path. So connected, there is another terminology we have in graphs, that is connected. And connected means every pair of vertices is connected by a path. Pair of vertices means um, uh, in each path we have pairs of vertices, and vertices are A, B, C, D, E, F. If you consider any path, if you consider a path where A, D, E, and F are available, as you can see, A, D, E, and F are an example of the path. Then A, D is basically pair, D, E is a pair, and E, F is a pair. So it's a definition of connected graph where every pair of vertices is connected by a path. And means any path you consider any path in which pair of vertices are available, that means that path is connected. And you can see it's not a connected graph, it's undirected, but it's not connected. Why we are saying it's not connected? Because you can see we have just break this graph into two pieces, right? So left side and the right side, right? So there does not exist pair of the vertices. So we cannot say that it's connected graph, because it's violating the definition of connected graph. And by the way, it's a It's an undirected graph. And there is another terminology available in graph, strongly connected directed graph. Every two vertices are reachable by a path. Not strongly connected, right? Strongly connected means when we have two vertices are reachable by a path, but in this particular example we cannot reach to the vertices which are strongly connected. This is again an example of not strongly connected graph. It's a directed graph, but it's not a strongly connected, because in this particular example we cannot reach by a path to every two vertices. So what is a strongly connected graph? And this is the example of strongly connected graph, where we can reach two vertices by a path. And if let's say, for example, if we are on A, obviously we can move to the B, we can move on a D, and we again come back on a A. And by using D, we can move on a E, and then E to F, and F to A, right? So there is a cycle available in this graph, and we again reach to every two vertices by a single path. So this is a strongly connected graph that we have on this slide. Now there is another example of graph, and as you already taught about trees, and trees are basically where we have parent nodes, and parent nodes have their children, and we have cover binary trees and complete trees and full trees. And on that particular examples, we just have seen that we, on each level we have two children on each parent node. But in graph we can say that a parent node can have more than two or three children. And you can see in this particular example we have a B, that is a root node, and root node has multiple children, and A, D, and C are basically the children of B. And furthermore, A has a child, B has, D has child, and C do not have any child. But in a graph theory, it allow you to connect multiple nodes in one single node. But in specific binary trees you cannot do that. You have a structure, you have a hierarchy where you have to convert, you have to divide your parent node into two child, and then further they split it into multiple childs. So but in a graph theory you can have multiple, or n number of nodes as a child uh, of one single parent node. And you can see in your real life, in your networking problem, in your roads, in your railway tracks, in your telephones, when you call, a single user can call multiple users, right? Single user can call thousands of numbers, thousands of users that he or she has in your phone book. So networks allow you to connect thousands of users in a single time. So this is a graph theory. In your laptop, in your computer devices, you can communicate with with your devices, with your components in a single click. How this data transfer into multiple devices? You have seen, you have experienced, you have used multiplexers, demultiplexers, you are using modem, you are using different type of device, electronic devices, which accept signals from different sources at the same time. How is it possible? This is only possible by graph theory. That means there is an algorithm, there is a procedure, there is a process used in that particular device that allow you to communicate, that allow you to send or receive signals in single time, and that allow you to communicate with multiple devices or components at the same time. So this is the tree, and that we can represent. Uh, this is a graph, but we can represent a graph as a tree. So this is a connected undirected graph without any cycle. There is no cycle available in this particular example. uh, this is again a tree. The graph that we have represent in the form of tree need to specify the root. Obviously, we have a condition in trees because we have to clarify where is the root node, who is the parent node of all the descendants of all the children. If we want to represent graph as a tree, then we have to specify the root node of the tree. This is the main preliminary condition while we are making trees, while we are converting the graph into trees. So there is another example of the tree that we represent. This is undirected, but it's a connected graph, and we represented graph in the form of acyclic graph. Acyclic means there exists there could be a cycle, or maybe not. Let's have a look. And as we can see, we have direction available. We can move from D to B, but we cannot move back from B to D. So it's not a cyclic path. That's why we are saying it's a cyclic graph, but it's a directed, right? So again, it's a graph, but you can relate it with the trees, right? Next, it's a complete graph. Different type of graphs. There is another type of graph. It's a complete graph. Why we are saying it's a complete graph? Because you can observe that each node is directly connected to another node, and when it happens, we can say we have a complete graph. And by the way, this is the example of your networks, because if you are using computers in your lab, if you are using computers in your net cafes, if you are using computers in your at your home, you are connected with everyone by using internet connection. Obviously, you can communicate with me, you can communicate with your friends, with your family members, with your colleagues. That means there is an architecture, there is a mechanism, there is an algorithm that allow you to communicate with multiple nodes, with multiple systems, with multiple computers at the same time. So how you can design such kind of complex system? uh, there must be a solution. There is a solution, obviously, and that is basically a graph theory. Graph theory allow you to perform or to design such complex systems. So in specific complete graph category, you can do that. What you need to do, you just need to connect each node with all other nodes. So this is a type of complete graph. Next type of graph is bipartite. Bipartite graph where every can be partitioned in a vertex u belongs to x and vertex v belongs to y. If you try to see in this particular example, this is a bipartite graph. In this particular graph, we can partition, we can separate a group to another group. Let's say if by look it look like a connected graph, but we can provide partition. We can split these nodes into multiple partitions. As you can see, if we want to separate A, E, C, and G. So this is basically connection between among A, E, C, and G. but again G is connected with B, and B is connected with F, and F has link with D. So there is no direct link between each node. There is a partition, but we have designed in such a way it look like a connected graph, but it's not connected. It's in a partition. It is in a partition, and we can separate these nodes with each other, right? So this is an example. This is the type of graph, and this is called a bipartite graph, in which we can partition our nodes into multiple sections, multiple, the modules. And these type of graphs are used in multiple real life applications, where we want to separate, we want to, to extract multiple functionalities of our systems. Then, if we talk about the applications, if we talk about uh, the usage of this graph theory in our real life, so we can see in transportation networks, flights, roads, etc. And as I already told you, in our real life, we have such systems, we have such problems in our life that we have to solve by using algorithmic solutions. And obviously we have flight simulation systems, we have transportation networks where we need to solve by using algorithms. We need to solve these issues by software solutions. And how we can implement these problems by using algorithms, and the only solution is graph theory. Graph theory allow us to connect each road with other road, right? Because obviously if we design this infrastructure in our country, in our cities, there is a plan, there is a mechanism that allow us to do that. And how we can map these roads, or the designs, we have to use a graph theory. So and if we talk about the flight systems they have their paths, they have their own tracks in a sky, in space, and they use their directions. And I use the word direction. They have directions, and they follow those directions, and if they do not follow the directions, they can have disasters, right? And obviously and you can see the example of graph theory in flight simulation systems, where aircrafts are driven automatically with autopilot, right? So all these examples are representing, or the showing the application of graph theory. Because in these systems the graph theory is implemented. And there is, and as I told you, we have algorithms, and we will cover in upcoming lectures that how we can use these problems, or how we can implement these problems with minimum time complexity, and to how to make an efficient solution of a particular situation, or a problem. And obviously we have communication networks, and the example is your phones. When you call from one network company, that is Jazz, or the other company is Ufone, how they are connected, how they allow you communication. Because one node, because Jazz is a node, Ufone is a second node, how they are connecting, how they are communicating with each other. Obviously there are protocols, there are rules and regulations that they have to follow, but to make communication between these two different companies, there is a solution, there is a mechanism, there is an algorithm that allow data communication between these two communicating devices, or these two communicating companies. And obviously we have web applications, We have World Wide Web, and web of what? Web of computers, web of digital devices, web of latest smartphones, right? So each smartphone, each computer device, each computer machine is basically a node. And how these nodes are connected with each other? By edges. There are edges, right? And edges make them connected, whether it's directed or undirected, right? And we have social networks. Obviously, there are applications that are using for social purposes, and obviously they are the example of graph theory, and how these social application or networks work together. There is a mechanism, there is terminologies that we can use, whether they can use cyclic path, they can use acyclic path, they can use directed graph, or they can use undirected graph. Then we have circuit designing. Obviously, we are dealing with electronic devices. We are using computer devices, and computer device is basically an electronic device. How we can how we can design this electronic device? Obviously, we have circuitry on our motherboard. Motherboard is an electronic component which holds millions of components, and how they fuse, how they communicate with each other. Because obviously, when we input our computer with the help of mouse or with the help of keyboard, that signal transmit from one component to another component. That means we are making communication from component to component. So there is a structure, there is an architecture that we use to make communication between components, whether it's from CPU to RAM, from CPU to cache, cache to RAM, RAM to cache. So there is a two-way communication process we have in our computer. And by using network theory, by using our graph theory, we implement these communication between CPU to cache, and we implement the communication between CPU and RAM. So we use graph theory to implement these complex electronic circuits, and we try to optimize our solution. We try to optimize the time complexity. And how we can reduce the time? By saving the execution time, by saving the space, by by reducing the memory utilization. And all these concepts we have already covered in our previous lectures. And obviously we have Bayesian networks. So these are all application areas we can implement these application areas. Most important and one of the most common solution of these problems that we can implement, we can solve. And this theory allow us to solve or implement these problems. And this is now for today's lecture. If you have any question regarding today's lecture, we have covered the graph, we have covered the directed or undirected graph, we have seen the example of simple path, we have seen the example of cyclic path, we have seen the example of connected graph, strongly connected graph, we have covered the example of bipartite graph, we have covered the examples of complete graph. And all these type of graph allow the data communication, allow us to minimize the time complexity, allow us to solve certain situations, certain problems in our real life. So thank you so much. If you have any question, you can ask to me. Take care.